Now shifting gears a bit, we have a pulley that's fixed, and I haven't drawn a big nail there, but I could. Don't want to ruin the board by actually driving one in, but you get the idea. This is fixed. There's something suspending it from ceiling or whatever. And you have two 300-gram masses suspended from that pulley. Well, it should be obvious that even if there's no friction at all anywhere, and that is going to be our assumption because we want to do the ideal case, that these masses are just going to hang there. Unless you got more mass on one side or the other, they're going to be balanced. Okay? So, we can draw our force diagram. We have 3 newtons here, 3 newtons here. And somehow 2 downward forces of 3 newtons keep everything in balance, although it looks like our net force ought to be 6 newtons downward and we got this mass, and why doesn't it accelerate? Well, it doesn't accelerate because this 3 newtons is really acting in the opposite direction on the system of this 3 newtons. This 3 newtons tends to make this mass descend so that this mass ascends. And this 3 newtons tends to make this mass descend and this mass ascend. And they have equal influence so that neither mass goes anywhere unless they also happen to be in motion. I say they'll just sit there. If it's originally just sitting there, it'll remain sitting there. If it's originally in motion, since there's 0 net force, there's nothing to change its velocity, and it will just continue moving in uniform motion until one mass hits the floor or the other hits the pulley, whichever occurs first. And of course, when that happens, you have other forces involved, and they do what they do. Okay, now the problem is, you want to understand this before you can really understand the full impact of the problem. Problem is, okay, we take 10 grams and move it from one side to the other. Okay? So we transfer 10 grams from one side to the other. Well, I could have done this on either side. I chose to transfer it from here to here because I think somebody said, well, let's transfer it that way. Okay? So now I have only 290 grams on one side, 310 grams on the other. So now the force on one side is 2.9 newtons, the other is 3.1 newtons. Well, now it's pretty clear that the force that tends to make this thing descend and this one ascend is greater than the force that makes this one descend and the other one ascend, so that this is going to tend to descend and this is going to tend to ascend. And you have a net force of 0.2 newtons acting on this mass. Okay? So, first place, it's not too hard to understand that the difference of these two forces being 0.2 newtons, you have 0.2 newtons acting on the mass of this system. What's the acceleration? Well, first of all, to find the acceleration, you know the net force. What's the mass? How much mass is being accelerated here? People will tend to want to use either this mass or this mass, but that's not right because both masses are being accelerated. So now the mass that's being accelerated is the whole 0.6 kilograms. Okay? It's not 20 grams either, because some people want to say, well, the 20 grams that you transferred. Well, yeah, it's being accelerated because it's still part of this system, but there's still a lot of other mass in the system, and it all has to be accelerated. So now we calculate our acceleration, divide our 0.2 newton net force by our 0.6 kilogram mass, and we get 1/3 of a meter per second squared, about 33 centimeters per second squared. Not a great acceleration, but see, we haven't transferred that much mass. Well, after a second, though, we'll be moving at 30 centimeters per second. Let's see, 30 centimeters about there, from here to here in a second, 1001, about that fast. It's going to be moving visibly after a second. It's going to be moving twice that fast after 2 seconds, and of course its speed will smoothly increase from the instant the system gets released. Now I assume we're releasing it from rest. That's kind of implicit. If it's already in motion, what? If it's in motion in this direction, where this one's descending and this one's ascending, then, well, since this force is greater than this, that's going to tend to slow the system down. Okay, and if the pulley doesn't get in the way or the floor, it's going to move until it comes to rest, then it'll start accelerating in the opposite direction. If it's already moving in the direction in which the force is accelerating it, then it's simply going to start with some velocity and build on that. Okay. Now there's a little more that I want to talk about relative to three-dimensional coordinate system, because you want to be thinking about this, and you're already used to three-dimensional systems and cross products. You did that in the first chapter of physics, and if you're doing multivariable calculus, you've done a lot more of it. So we'll talk about that for a second.